women in STEM. They have a ton of awesome activities for like professional, social, leadership development. They go to conferences, they do workshops on all kinds of things, they do K through 12 outreach, a bunch of volunteering, they do professional networking events. There's one coming up on September 28th, and it's called Evening with Industry, and basically you pay $10 and you get a 3-course meal and you get to dine with industry recruiters and professionals, and it's people from like IM Flash, Chevron, I'm forgetting. It's a bunch of really big name companies around this area, and they are actively recruiting engineers. So that's a really awesome opportunity. Again, that's on September 28th, but if you're interested, you should sign up as soon as possible, because the sooner you sign up, the better chance you get of getting seated next to somebody you want to be seated next to. So, yeah. It's called Evening with Industry, and it's put on by Society of Women Engineers. So if you're interested, you can come to our social. There's a little informative flyer up here. It's on August 31st. It's an ice cream social, so it should be great. And I have some flyers up here that have a link you can go to get onto the mailing list, and that will also be sent out with more information. So August 31st, I hope to see some of you at our social, and then September 28th, Evening with Industry. Thanks.
Awesome. And did I miss it? SWE's not just for girls, right? Anybody can go.
Yeah, anybody can do it. Anyone. It's just the goal is to support women in STEM, but they do events that anyone can come to.
Okay. And I'll just say that some of the people in our department that have been like the top students have all had SWE all over their resume, right? So I think it's a great organization. If nothing else, it's going to put you next to people who are doing great things, I think. And so I think you should go to that. Okay, before we get started, one more plug for the TAs. Most of them, the two that haven't been able to attend, they have a class that conflicts, but Friday they don't. So I want to introduce them real quick. So Megan, Emily, Josh, who else am I missing? Christian, I think, is in the lab. And David, are you here? So we have 3 of the TAs. So I want to put in a plug to attend their hours. Like I said, we're going to move most of the homework, like if you're just stuck on homework, we'd like to move a lot of that to Canvas. But these guys do great sessions, like where they're going to overview stuff, they're going to remind you how to take hard integrals or derivatives, they're going to teach you more of the stuff here. They're going to say, hey, I took this class from Sparks last year, and here's what he tested on, right? Stuff like that is like really valuable. So I really am going to put another plug to attend their office hours, because I think you'll learn a lot. Okay. That said, we will get started. Today we're going to wrap up just a tiny bit left on Chapter 2, and then we're going to jump into Chapter 16. Okay, so last time we left off, we were talking about this potential energy well. We called this a potential energy well because it's kind of well-shaped, right? And we had a couple things that we learned about it. First off, we said the deeper it is, the more symmetric it is. We said the deeper it is, the higher the binding energy. That makes sense, right? Because the binding energy, this red line here, that's just how much energy you'd have to overcome to pull these things infinitely far apart, which is just another way of saying melting it. It's no longer a solid, it's now melted, okay? And then, so what we have left to do is we correlated this to thermal expansion. Let's talk a little more about that as it relates to other materials. We gave an example. We said a metal versus a ceramic versus a polymer. These things have different thermal expansions. So therefore, what can we say about the shape and the depth of this potential well? So turn to your neighbor and give them a thought. How, if you had to sketch, in fact, with your neighbor on your piece of paper, sketch polymer, ceramic, and metal to the best of your ability for these potential wells. Polymer, ceramic, metal. Okay. Anybody feel brave enough to come up and sketch it for us? Anybody feel brave? Maybe a little bit. Come on up, come draw for us. I'll draw the axes for you. I'll give you a head start. She's like, why do I make eye contact? Okay, come on up. No? Okay, that's fine. Anybody feel brave? Want to come do it? Come on up. It's Simone, right? Simone? Simone, come on up. Okay, we're going to draw, ceramic will be blue, we'll make metal green, and we'll have polymer be red. So give us your best sketch. And kind of your thinking behind it. And if it's wrong, that's okay.
So
you've got,
last class
you're plotting energy versus distance here. You're going to draw your potential well.
What color am I?
Oh, you're currently at red, so draw your polymer.
Okay, so I think that polymers are going to be
okay, there's polymer.
Okay, and then
now let's switch it to blue and do ceramic.
And ceramic will go deeper.
Okay.
It'll be more symmetrical.
Okay.
And metal will probably be somewhere in between.
Yeah, you're fine. You're fine. That's perfect. That's perfect drawing. That's exactly right. His thinking was right. You heard him. He said two things. Ceramics is going to be deepest and most symmetrical. Polymer will be the least, and metal will be in between. Right? So how did you know that? What was your line of thought?
I just thought that with ceramics, we talked about it on Wednesday. They don't expand a lot. They're a little more, I guess, a little stiffer. They can handle a little more heat.
So stiffer tells you that where does that show up on this curve? That's the hardest one. It's going to be.
Because it's the deepest.
So stiffness shows up at R equals R naught right here. It's the slope of that line. So that's going to be the radius of curvature at the bottom of your well. So if it's really narrow, that's going to be the stiffest. That's a hard one. That's okay. What else did you have to go off of when you drew these?
And then
I'm going to clean them up a little bit, but they were right.
Polymers were a little more, I guess, they expand more easily. They're a little less stable than ceramics. And then also we mentioned last class that they're not symmetrical. So you're going to have a shallow well, and then
Melting point is one thing to look for. We know that ceramics melt way higher than polymers and higher than metals, so they have to have the deepest potential well, right? Metals are in between than polymers, right? So this radius of curvature, that's proportional to the stiffness. That's the hardest one to think of, I think. So what are some values for this coefficient of thermal expansion? If you take this class, you should have a few ballpark numbers in your head. Things like coefficient of thermal expansion. Obviously, every polymer, every ceramic metal is going to be different. They're all unique. But what are some order of magnitude values that you should know? Let's start with polymer. The rate of thermal expansion should be on the order of maybe 100 ppm per K. ppm is parts per million, so it's just a unitless way of saying whatever the number is times 10 to the negative 6. So for every degree Kelvin that you increase, the strain, right, is going to be on the order of hundreds of ppms, okay? For metals, it's going to be something like 10, maybe 10 to 100, and this will probably be less than 10 for ceramics, right? Around even 1 on some of them. In fact, some ceramics are terrific because they have the coefficient of thermal expansion that's negative, meaning you heat it up and it shrinks a little bit, it's unusual, or 0. Quartz, like if you've ever used a quartz or like a crystal, right? If you have fancy glasses that your grandma gave you and it's crystal, all that is it's a crystalline form of SiO2, which is what we call glass, right? It's actually quartz. We'll talk way more about that later. That material has almost no thermal expansion, so you can take it, even if it's a long rod, and I can torch one end until it's glowing white hot, and it won't break due to differences in thermal expansion in the rod because there is no thermal expansion. That's terrific. I can take that same rod while it's glowing white hot and dunk it in water and it won't fracture. If I did 99% of the other materials, they'd all break if you did that, okay? So that totally ties into what we talked about before. It has to do with the shape and the symmetry and the depth of these potential wells, okay? We'll talk more about composite properties later. Let's talk about bonding very quickly. There's different types of bonding. I'm going to expect that you've learned this in chemistry before. There's ionic versus covalent. There's van der Waals, right? What are the characteristics? Somebody remind me, or remind your neighbor real quick, what's the difference between these 3 bonding types? Go ahead, talk. Okay, so somebody help us remember what are some of the characteristics or differences between these binding things. Let me ask Cope to pick. Let me pick on Cope for a minute. Tell us something that comes to mind.
We were just saying, like, thinking about ionic bonding, sodium chloride. There's an example.
Okay. How might that be different than, say, so sodium chloride versus something? Give us an example of a covalent one. Can you think of something?
Well, I guess it's the difference between sharing and kind of like taking one.
That's the key feature. Ionic does not share. Sorry, I'm running the screen capture and it's making my pen not show up immediately. Does not share, whereas this does share. So if it doesn't share, it kind of gives it away, right? It doesn't exactly give it away. It means it doesn't care very much about it. It's holding on to it much, much less tightly. We'll say that, right? So sodium chloride, we remember, if we pull up our periodic table, right? If we go to like here, pull up my favorite periodic table, you'll see that sodium, it is one electron away from being in a state that it wants to be. So sure, its electron, it's not going to hang on very tightly. It doesn't like throw it away. It still holds on a little bit, but not very much. Whereas chlorine really, really wants to get that one more, right? So something that would share, give me an example. Anybody think of something that would share rather than give away? Matt?
Like glucose.
Glucose. What's the bonding roughly in glucose? Or can you give us, what's one bond that is present?
Well, it's carbon and hydrogen.
Yeah, carbon and hydrogen, plus the backbone. Glucose is going to have some sort of polymer chain. We'll talk more about these in chapter 4. I give them shorthand, going like this, where every time there's a change in direction, that's a carbon. So basically it's a carbon bonded to carbon. Oh, my Facebook update. Thank you for that. Good little class. So carbon bonded to carbon, why would that be a covalent bond? Right? Carbon over here, why would it share rather than give away? It's right in the middle, exactly, right? How many electrons does it have? 1, 2, 3, 4. It wants to get to 8, so it's not going to give away 4 to get to 8, right? They're going to share instead. So that's the difference between ionic and covalent, is whether it has to do, if for example, if Simone is a sodium, and he's bonding with, what's your name again? Mark. They're bonding, and it's ionic, then Simone gives him the electron, and he's like, I don't really care what you do with this, just take it. And Mark's like, dude, I just need the electron. We don't have to talk anymore after this, right? That's ionic bonding, okay? Now, covalent bonding would be different. That'd be like Megan and Emily over here. They both want something, so they're going to put it right between them. And if Emily says, I'm going to move this over here, Megan will get mad. She's like, no, that has to sit right there. It's like my 2 kids with an iPhone. Like, they both want like right perfectly between them because they're sharing it, right? And if one takes it more than the other one gets upset. Right? So it's directional, and it has to stay put between the 2 atoms. That's a key feature, and we'll come back to that later when we talk about crystal structure. That influences what type of structures can form. Okay, and then van der Waals, or sometimes called van der Waals. Well, there's metallic. Obviously, metallic means that it's just delocalized. That this whole room, imagine there's beach balls bouncing around. That's kind of like metallic bonding. They don't really care where they're at as long as they're in the room, right? Who has them? As long as they're not too clumped together, it doesn't matter, but they sort of spread out. Van der Waals bonding, what's the difference there? Anybody remember van der Waals? They sometimes call it secondary or, yeah, Simone?
Isn't it there's a temporary dipole?
That's it. The key word there is dipole. What's a dipole?
When all the electrons are located at like some point on one end.
Let's take a big atom, something like uranium. Uranium has like oodles of electrons, right? It's clear down here at 92. It's got 92 electrons, right? So at any given moment of time, if I took a snapshot, sometimes they call these snapshot dipoles, those 92 electrons won't be perfectly symmetrically around it. You might have like more on this side at that second in time, right? If there's more electrons over here, then you have a dipole that goes like that, meaning you have a net positive over here and a net negative temporarily, right? So you can have individual atoms that have that. You can have molecules, right? What if you have like carbon bonded to fluorine, right? Which one of those 2 atoms wants the electrons more? Fluorine. So this is like my 5-year-old and my 3-year-old sharing the iPhone. My 5-year-old's going to grab it a little bit closer because he's stronger than the 3-year-old, but the 3-year-old still got her hands on it, right? So there's a net, like there's a dipole right here, net negative. I drew that wrong. Should go the other way. Right? It's net negative there and net positive by the carbon. Right? Overall, the charge is still the same. It's just we have a slight charge separation. Charge separation is a dipole. It means that there's a tiny little chance for Coulombic interaction, right? So where do we see evidence of van der Waals bonding and why is it important? Yeah, remind me your name. Jan.
Like so water molecules in a glass might have some attraction between the two.
Absolutely. Water is a molecule that looks like that. You've got your O and you've got your 2 H's. It's a bent molecule. That's the key feature because it has lone pairs left over from your oxygen. So it's a bent molecule. So why would this be polar?
You have a concentration of electrons heavier on one side of that molecule.
Yeah, you've got slightly delta negative, delta positive. Because your oxygen wants the electrons a little bit more, it's more electronegative. And so that whole molecule, that bent shape is polar. So another one can stack underneath it. Another one can stack above it, right? And so when water solidifies into ice, it actually has to abide by these rules of being a polar molecule, and that's how it bonds together. We'll talk more about that later. And polymers are another one, right? I just showed you, like, Matt mentioned glucose, which is just a type of polymer. So we'll draw these like that. Oh, that's not showing up right away. Right? But these things, they, along the chain, are covalently bonded. Those are strong bonds. Like diamond is covalently bonded. Diamond melts at like 3,000 degrees or something crazy like that. This polymer, even though it's got the same bonds as diamond, melts at 100 degrees. What's the difference? Well, when it melts, the bonds along the chain don't break. What does break? The bonds between different chains, right? There's a bond, like maybe this is like slightly positive, that's slightly negative. And so there's this weak van der Waals bonding, VDW. Van der Waals bonding between the chains. That's a really much lower strength bond than a covalent or an ionic bond. So it's easy to break. Therefore, you get very, very low melting points when things are secondary or van der Waals bonded together, as opposed to, held together by ionic or covalent. Okay, we'll talk more about that over the whole semester. I want to introduce the concept for now. Let's shift gears and talk about thermodynamics. So the learning objectives are, we're going to talk about what is enthalpy, what is entropy, what are their roles in thermodynamics, what is thermodynamics first off, and then we're going to predict entropy for a couple different reactions based off of phase, size, atomic number, etc. Okay? So thermo is not covered in this book. I wish it were. The guy who wrote it doesn't think it's important, but I think it's one of the most important things in material science. Why? Because we said earlier that what is the reason why anything happens in material science? If it lowers energy. And you cannot talk about whether something lowers energy or not if you don't have a grasp of thermodynamics, because that's what describes energy, right? So we're not going to do a full treatment like you'd get if you're mechanical engineers, you're going to get a full course on that. Material scientists as well, I don't know about civils, maybe, right? But you're going to learn more about it later. I'm just going to give you the abbreviated important version, right? Since it's not in the book, we have to look towards outside sources. I think there's a really great web tutorial at Wisconsin. It goes through all these topics. It has like punch-in values to check if you're right sort of thing on their website. It's great. There's another one at Purdue. If we scroll way down to the end of this presentation, I've got a link to the one at Purdue. Ken at Purdue's also got a really good one on free energy. So either these resources or just Google it on your own are great resources. Plus the course notes should get you through it. Okay? That said, what is a chemical reaction? It's a process whereby one substance changes from one form to another. Okay? In this class, we're going to ignore reactions where there's a change in nuclei, things like radiation. Radiation, like you got uranium, and it's giving off particles that are neutrons, right? So it's changing the isotope. We're going to ignore those. In our case, all we're doing with our reactions is exchanging electrons, either sharing or giving away, right? We're forming weak dipoles, okay? Why do we care about these reactions as material scientists? Why do you care about them as mechanical engineers or civil engineers? Somebody give me an idea. Why should you care about chemical reactions? Yeah, Eric.
Affect the properties of the material you're working with?
Yeah, absolutely. Why should a mechanical engineer care?
Material selection.
Material selection. How about salt water? We're civil engineer, right? You're going to build a bridge and the trusses go down into like salt water in an ocean or something. What's that salt water going to do? Is it going to corrode? Is it going to react? Right? We want to know reactivity. Are you going to use are you making hypersonic engines, right? For the future of flight might be hypersonic flight, so much faster airplanes. What will happen with the heat? what will the materials happen when they're exposed to that crazy high temperature in air, right? They're going to oxidize, they're going to melt, right? All these are reactions, so you need to understand just a little bit about them. So that's why we're talking about this chapter. How do you write them? In this class, we write reactions going from reactants to products. And notice that key figure there is that it both goes to products and it goes back. A simplistic version of this, when you took your high school Gen Chem class, you say reactants go to products. But that's the wrong way to think about it, I think, because all reactions have an equilibrium, right? Every one of them. And you'd say, well, what if I take a little bit of gasoline and I light it on fire? The gasoline's combining with oxygen in the air to form H2O and CO2. Are you telling me that there's a equilibrium in which it goes back? Yes, I'm telling you that. That there's an equilibrium. It might be really, really small. I remember when I was in my Gen Chem class in college, we figured out the rate at which your teeth are dissolving and then redissolving back on. And it turns out to be a very, 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 very small number because your teeth are evolutionarily designed to not dissolve. But there is a rate, right? So there's a rate of coming and going with reactions. That means that there's an equilibrium point. When you reach equilibrium, it's not that the reaction stops, it's that the amount of reaction going forward is now equal to the amount going backwards, right? And you've reached equilibrium, okay? So boiling water, when you're boiling water, there's as much water leaving, going into water vapor, as there's water vapor turning back into liquid, right? It's at equilibrium. Okay, some reactions, well, we said that they're going to involve electrons. Sometimes they actually transfer electrons entirely, right? For this, these are called redox reaction, meaning reduction and oxidation reactions. The thing to remember here is some terminology. Oxidation, if we talk about oxidation in this class, that's loss of electrons. Reduction is gain of electrons. And I don't know about you guys, but I learned oil rig in high school. Whatever helps you remember this, oxidation is loss, reduction is gain, right? More terminology. The cathode is the negatively charged electrode where reduction takes place. So if you've got two metals that are going to react in a redox reaction and one has reduction taking place, you know immediately that's the cathode. Therefore, the other one must be the anode, which is where oxidation takes place. Anode is where oxidation occurs. Okay, so anode and cathode are important terms we'll talk about. Let's talk about the electrolysis of water, right? What is electrolysis? Have you heard that term before, electrolysis? It's literally like you take if I had a beaker of water and I put like an electrode in on one side, right? An electrode on the other side, and I pass the current through it. I'm going to be able to convert some of that water to its constituent elements. I'm breaking bonds, basically. So I'm going to be able to form hydrogen and oxygen, right? So if we start out with H2O, right, and that's maybe in the liquid form, we're going to be able to form H2 gas. The subscript L is liquid, subscript G over here is gas. And we can't form 2 moles of gas, so we have to form 1/2 of a single, O2 molecule. Go away. Running the camera is making this run really slow. Okay, right, so that's our reaction, okay? So does this involve redox? Does this involve transfer of electrons? Yeah. How do we know? How do we know that this involved a transfer of electrons? Well, consider what it was before for you guys, and then what it was after, right? So before, what was the charge of our oxygen? What's the charge of oxygen almost always? 2 minus. Therefore, we have hydrogen. What must be its charge since there's 2 of them? It must be +1, okay? This is +1, 2 minus. Over here you've got an H2 molecule. This is chargeless, right? And this one also is chargeless. So they went from being cation and anion to being no charge. So they must have exchanged some electrons. So we can write out what are called half-cell reactions. Half-cell reactions is simply where you write out what's being oxidized, what's being reduced, right? So let's write them. We're going to say that H plus, right, aqueous, our aqueous H plus ions are going to go to form, skipping steps. This is not working very well. Plus 1 electron. If we add an electron to that, we can form half of an H2 gas, right? Alternately, we can take our 2 H2Os that are liquid, and we can form O2 plus 4H plus 4 electrons, right? So in one case, on the left-hand side of the equation, we have adding electrons. In the other one, it's on the right-hand side, so it's a product, so it's losing electrons, right? So the hydrogen and oxygen respectively have half-cell reactions. So let's talk about balancing equations. Balancing equations, you guys should have seen this at some point. I don't think we're going to do this in class. I'll leave this to the TAs to go over this if you can't remember. But equations have to balance, meaning the same number of constituents on your reactant side have to be present on your product side. So if I look at this, iron plus chlorine gas forming iron chloride, this is not balanced because there's 3 chlorines here and 2 here, right? So you have to balance this, and you have to say, what's the common denominator? You'd say that there must be 2 here, 3 here, 2 here, right? To make that balance. So the TAs will do more examples of that if you have questions. We're going to skip it. I'm going to assume that you know it from Gen Chem. Okay, finally we get to the most critical question, which is how on earth do we know if a reaction will go forward or not? So the answer is definitely, in fact, in this class, if you're ever not sure of the answer on an exam, you're always the safest bet is to write energy or something about reducing energy, right? But that's a generic term right now. Like, what do we mean reduce energy? How do we know what the energy is, right? That's all fine and well in like a very qualitative way. But to be quantitative, how do I know whether if I put a piece of metal in salt water, if it's going to corrode? How do I know, right? We have to actually have measurable quantities, and that's where thermodynamics comes in, right? So thermodynamics, before we get into it, it's the study of heat as it relates to energy and work, right? We have to introduce a few variables. The first one is temperature. So temperature, if it's constant throughout a system, so it's in equilibrium, then we have thermal equilibrium. If pressure is constant throughout a system, then you have mechanical equilibrium. In this room, do we have mechanical equilibrium or do we have thermal equilibrium? We have mechanical because we're all at, not sea level, we're at like 4,500 feet, right? And there's the same atmospheric pressure in this room. So the room is in mechanical equilibrium, but it's definitely not in thermal because every person's probably a little bit different temperature. We've got vents, so that's pushing cold air and it's getting moved around. It's maybe close to thermal equilibrium, but we're definitely not there yet, okay? In fact, technically mechanical, there's like, your bodies are under slightly different pressure. Your ears, that's why your ears pop. They can have different pressure, right? Anyways, there's mass, there's volume, and then there's this U, which is internal energy. Now you'll remember that, or maybe hopefully in physics they told you that energy can neither be destroyed nor created, right? Energy just is. You can translate it from one form to another, but you can't destroy it. And that right there, that sentence, is a recap of the first law of thermodynamics. The first law of thermodynamics is simply that the total change in energy is equal to heat added minus work done on surroundings. Right? It means we didn't destroy energy. If the internal energy of this blow dryer changes, it's because what? It either had heat go in or out of it, or it did work on its system, or both. Right? So we can write that. When we write the first law of thermodynamics, we're simply writing that that the change in internal energy, so du, must equal heat going in or out, so change in heat, dq minus pdv. That's work, right? The change in volume at some given pressure, right? That's work done on the system. So that's the first law of thermodynamics. It's pretty simple. It just is that we don't destroy or create energy. It just transfers from one form to another. So when people say like when you generate energy from like a power factory, you're not generating energy. You're converting it from bonds in carbon or bonds in natural gas or energy from the sun, photons, to just another form, right? By either spinning turbines or your solar cells doing what they do. We'll talk more about that later. Okay, let's skip that for now. Let's talk about enthalpy then. We need a new term to talk about energy because whether, when we say a reaction happens or not, it can't just be about the material itself. It has to take into account the larger system, right? So the internal energy is not the right term to minimize. There's another term we have to minimize. So to get to there, we have to introduce enthalpy. Enthalpy is a measure of the total energy of a thermodynamic system. Now we're talking. That sounds more like something that we're interested in, right? The total energy. And so it's going to be equal to, it's called H. We're going to call it the internal energy, U, plus PV, right? The energy of the system, the work on the system, right? So what's the change in enthalpy? We have to take the derivative of this. There's a catch. What do we have to do when we take the derivative of something that has two variables that can both change? What's this called? Yeah, from calculus, you remember you have to go dH equals du, so the change in internal, plus P dV plus V dP, right? We have to separate those and take them independently, right? And then add them up. So that is useful because this right here, that was just dq from our last equation, right? We said that dq, if you bring this minus pdv over, so du plus pdv, that's just the heat that goes in, right? So the change in internal energy plus work, that's just our heat. That's great, that makes our life easy. So that means measuring enthalpy, all we need to do is measure heat change plus VDP. So that's the volume and then the change in pressure. Well, most reactions, not all, definitely not all, but most, especially the ones we care about, happen in air, right? Happen in air in ambient conditions, meaning that pressure, is there pressure change? Nope, no pressure change. So this goes to 0 if no pressure change, which is good for a lot of things, right? Not everything, but a lot of things. We're at constant pressure. Constant P, okay? That means for enthalpy, if you want to measure the enthalpy of a system, all you need to do is measure what? The heat in or heat out, okay? This should sound familiar. This is something that you would have learned about in chemistry. This is the enthalpy of reactions, right? It's just the heat that's absorbed or evolved in transforming from reactants to products at a given temperature and pressure set, right? In fact, you're probably familiar with terms like this, like exothermic. Exothermic means that heat gets released, and endothermic means that heat is getting absorbed. Enthalpies are additive and reversible. I'll talk more about that in a second. It has to do with Hess's law, so we'll come back to that. So the question is, which one of these favors whether or not a reaction happens? If I've got a reaction, you know, gasoline, and I'm going to combust it with air to form water vapor and CO2, is that exothermic or endothermic, and is it spontaneous or not spontaneous? It's exothermic and it's spontaneous. And there's an activation energy, but it wants to happen, right? And it wants to happen because it's exothermic. We have this idea that exothermic is always favorable. It's actually not the case. At low temperature, low T, exothermic is favorable. But at high temperature, actually endothermic can be favorable. Why? What do you guys think? Has to do with something called the Van 't Hoff equation. Van 't Hoff equation basically talks about equilibrium constant, which we will get to by the end of today, the equilibrium constant, as it relates to changes in temperature. I think the easiest way to think about this is if you have a reaction that's creating temperature, right, then you can think of temperature as a product of the reaction, right? So just like we had before, we have like reactants and products. And if you have too much product and temperature is one of your products, meaning it's at a high temperature already, and you're trying to add more product, you're trying to push it even further towards past what its equilibrium might be, right? Whereas the other way around, if the room is cold and you're giving off a product which is temperature, then you're not fighting against equilibrium, okay? All right, so that's enthalpy. That's the first tool we need to figure out energy. We need to know about enthalpy, okay? Which is heat evolved or absorbed during a chemical reaction. But there's another, so first off, why can we say that some reactions, like ammonia, for example, when they create ammonia, it's called the Haber-Bosch process, it's critical. It's probably the most important reaction on this planet because it creates fertilizer, which we all need to survive because that's how we grow our food, right? The Haber-Bosch process, invented in like the 40s. Isn't that crazy? Something that we all could not live without on this planet was invented in the 40s. Because 7 billion people, there's no way there's enough food without fertilizer. Anyways, it does not work at high temperatures, right? It shouldn't work. And it's endothermic, and yet they do it at high temperatures. So that means that there's something else there that we're neglecting, right? There's another term from thermodynamics that we haven't talked about that must be involved, and there is. It's called entropy. Entropy is the number of specific ways in which a system can be arranged. And it's sometimes, in this class we're going to talk about quantitatively, or qualitatively, I should say, as a measure of disorder. So if I've got a big paint bucket, and I fill it full of marbles, red ones, right? If I shake that up, that system, and I look at it, it still looks like a bunch of red marbles. We agree? If I take that same paint bucket, and I fill it half full of white marbles, and then on top of that I fill half full of red marbles, I shake it, what's happened? It's mixed. Will it ever, is there conceivably a scenario where if you took 100 paint buckets, a majority of them, after you paint shake them, will be separated into white and red again, if they're the same marbles? No way, right? We inherently know that, it's true, right? If you take your Kool-Aid and you pour it into the giant pitcher to make some Kool-Aid for your 5-year-old, there's no way that that's gonna happen to just completely demix into a powder and liquid again. Even though we say that like, there's reactions, atoms are bouncing into one another all the time, and statistics and large numbers, we just inherently know that things tend towards disorder. Anybody who's watched Jurassic Park, if you guys were alive when that came out, knows, thanks to whatever his name was, what's his name?
Malcolm?
That wonderful, yeah, that's right, Malcolm. That that chaos theory says things tend toward disorder. That's just basically saying the second law of thermodynamics. The second law of thermodynamics says the change in entropy, ds, S is our entropy. If we could put a number to it, we can. That's weird. It sounds weird to be able to put a number to entropy, but chemists have found a way to do so. And the change in entropy is going to be equal to the integral dq over temperature, and that must always be greater than or equal to 0. That's a really mathy way of saying that entropy must always at least be constant or increase. The disorder must always at least stay the same or increase. It will never become more ordered spontaneously. And so somebody give me an example that's contradictory to this. What's something that looks like it orders? When do you order something? Yeah, what do you think? Remember your name.
I kind of, Rob.
Rob.
I kind of have a question with my...
Yeah, go ahead.
Because when you were talking about like the Kool-Aid powder or something like that,
Yep.
I'm just trying to think of a theoretical example where maybe it's dissipating to the point that it goes to a homogeneous mixture, and that it's perfectly distributed at that point. So that disorder is kind of order of its own? Is that...
I don't think I follow you. One more time.
You don't follow? Okay, so I'm just thinking about it. In certain situations, when you mix two things together,
Okay.
they mix so perfectly and so evenly
That it becomes a crystal, and we will talk about
and then
that.
it's
So take sodium and chlorine atoms. When you make salt, those things aren't just like randomly all over the place. That's called an alloy if they're random, but they arrange. It's like sodium, chlorine, sodium, chlorine. So that is a crystal, and that is more ordered. You've actually gone up in order. We'll talk about that. That's an excellent observation. Okay, let's do an example real quick. I have some rubber bands. And cover your eyes because I'm going to flick these willy-nilly through the classroom. And if it hits one of you, grab one. I'm going to have you do an experiment for us. This is a great idea for a pre-tenure professor. We were going to give you tenure except for that elastic band in the eye situation. I'm not even close to you. I'm sorry, guys. Maybe. Oh, there it is. Okay, so if you've got a rubber band, what I want you to do, give it a couple pre-stretches because these are right out of the bag. So you don't have to worry about them. I'm going to have you put it on your lips in a minute, but they're brand new. The bag is right, I just opened it. Okay, so give it a couple pre-stretches because they come a little bit weird when you first get them. Then what I want you to do is, your lips are really sensitive to temperature. So on your top lip, go like this, and then touch it. Okay, let it equilibrate for a second, and then let it go. And tell me what temperature you feel in the rubber band. When it goes from stretched, hold it there, let it down, what do you feel? It gets cool, right? And when you go the other way, it gets warm. It's harder to tell when it's getting warmer. It's easy to tell when it gets cool. This is the most ridiculous looking demo ever. I feel like this is ridiculous. But there's a point to this. And I'm going to have you do a clicker thing to show you the point of this. So the clicker thing, I'm not loving turning technologies because it won't work. It's broken currently. They're trying to find a solution. So in the meantime, we're going to use polleverywhere.com. What I want you to do is go to, let me start this. If you go on your phone or laptop, this is not for phones. So if you don't have any of these devices, don't sweat it. But if you do, go to pollev.com/dandypants327. I did not choose that. For real. Like that was generated. I didn't do that. pollev.com/dandypants. And I want to ask the following questions. So first, as you stretch a rubber band, do you break or form bonds? Doesn't matter if you get it right or wrong. What do you think? I assume that you can be logging in answers. I made this a long time ago. I hope it's still active. I made it this morning. Oh, okay, I got to activate. Okay, sorry, I unactivated it earlier. So, do you break or form bonds? People are changing their minds, jumping all over the place. Most people think break, it looks like. Okay? Okay, that's the first question. We'll come back to this in a second. Okay, next question is, all right, everybody feel like they've gotten a chance to answer? There's no points here. Soon we'll have points.
What's the argument?
What's that?
There's a maximum.
There's a maximum number it can be.
Oh, that's okay. We're going to keep going. I did not know that. Soon we'll have our clickers working. Next one is breaking bonds is what type of process? Endothermic or exothermic? Type in A or B, or hit the A or B button. Poll is full. That's funny. I wonder how many it even allows us to do. Anyways, so most people think exothermic. That's right. Next question is, when you take a heated stretched rubber, sorry, when you take a stretched rubber band, stop. I don't need to see this. Okay, if I take a stretched rubber band and I heat it, what's it going to do? This one's harder. I have a stretched rubber band right here. And maybe we can get this to work. Okay. Don't let me down. There I am. Okay. There you guys are. There's our thing. Okay. Wait for it. You can see a ruler here. We're going to compare the bottom of this thing with the ruler when I hit it with my wife's travel blow dryer, which if I ruin, I am busted. Has to come home with me. Okay, I'm going to hit on hot. What's going to happen though? Log your answers if you still can. What did most people think? Can I do this? Most people think it will stretch. Okay, fair enough. What's going to happen here? Right now it's reading, since we're not barbarians, we're going to read it in centimeters, not inches. It's at 17, right? Ish, you guys see that? The bottom of it, more or less? Okay. It is going up. It's at 6. It's at 17 and a half, which means it's going up. Right? It's actually shrinking. And then if I move this, sorry, put that back. It stretches back down to 17 when it cools off. So what the crap is that? Right? That flies in the face of everything we know and love, right? Because think about it. I just said, what did I say? Which one's spontaneous? What reaction is spontaneous? If I take this and I stretch it, is it spontaneous for it to stretch? No. It's spontaneous for it to shrink. When you felt this thing on your lips, right, like this, and you let it go, it got cool though, right? So the spontaneous reaction, the one that happens automatically, is one that absorbs or gives off energy. It must be absorbing, so it is endothermic. So I just gave you an example of a spontaneous endothermic reaction, and it's at room temperature. It's not at any high temperature or anything funny like that. That's happening at room temperature. So everyone in this room should be saying, the universe can no longer exist. Like, this cannot work. Like, it's impossible. So somebody tell me what's going on. Why did 64% of you get it wrong?
Stretching, you're kind of pulling some bonds apart, I would think. And when it comes back together, they're reconnecting and releasing energy.
As you stretch it, you're pulling bonds apart. That's right. Yeah, you're right. As you stretch it, you're forming bonds. And I'll show you why in just a second.
Is that why it becomes stiffer as you stretch it further?
There I am. It's still going. Okay, so what's happening? Somebody explain this to me. It has to do with entropy, right? In fact, there's two driving forces in the universe. It's not just heat. It's not just enthalpy, right? Enthalpy is important, for sure. In fact, most of the time we only care about enthalpy. We just say, is a reaction spontaneous? Well, is it exothermic or endothermic, right? That's all we ask. But in fact, you can have a reaction that's spontaneous, but its main driving force is not enthalpy, it's entropy. So, where does entropy come into play with a rubber band? What do we mean by order and disorder? Where is order and disorder changing when I stretch and release a rubber band? Because a rubber band is driven by, it goes from this to that due to entropy. So this must be the more disordered state. This must be an ordered state. How? Anybody got an idea? After chapter 4, you guys will all be able to answer this question. But anybody have a thought right now? Give us a shot, Dennis.
So when you stretch it, the chains, they lengthen, the polymer chains lengthen, they get lined up, it becomes very ordered, but if you release it, they can kind of do whatever they want.
Bingo. Dennis is a chemist, so he had the inside track a little bit, right? So that's exactly right. Polymers, including rubber bands, are made up of long strands of, covalent bonded materials most of the time, but they don't stay long like a rope. They look like a climbing rope if you just throw it in your bag where it just kind of is like a jumble together, right? They don't stay long like spaghetti strands that are uncooked. They stay jumbled like spaghetti that has been cooked, right? Therefore, this is a jumble of spaghetti strands all mixed up. We'll talk way more about this in chapter 4. And when I stretch it out, I force some of those to line up with one another. And in doing so, I make it easier to form bonds. I do this, right? You've got things that are stretched out, so now they kind of sit next to each other, and it's easier to form these van der Waals bonds than if it's just kind of all over the place, right? That's harder to form bonds. We'll talk more about this in chapter 4, but for right now, I just want to introduce the two concepts, enthalpy and entropy. So one more time, and Eric, first question.
Oh, so I just related to these bonds forming, does that have to do with why the rubber gets stiffer as you stretch it?
Exactly, because, like, let's say that this is my polymer. I've got a bunch of these strands, right? If I want to, like, stretch it, I start pulling on it. Soon they're all lined up, and then for me to stretch it further, I have to start breaking bonds, right? And that's a lot harder. Like, untangling is easy. That doesn't take very much force, but breaking bonds is harder. So that's kind of the right way to think about it. Yeah, it's that orienting polymer bonds is relatively easy. Breaking them is harder. So in chapter 8, when we get to deformation mechanisms, we'll talk way more about that. There's a few more steps there, but that's exactly right. Okay, so to recap, two forces in the universe, right, that tell us whether or not something happens. It's not just energy. We now have decided that energy has two components. On one hand, we have enthalpy, which is heat going in or out of the system. It has to do with breaking bonds, right? On the other hand, breaking or forming bonds. On the other hand, we have entropy, which is tendency for materials to want to be disordered, right? And so which one wins out? That's the next question we should ask. Like, why is it that in Gen Chem they can tell you the spontaneous reaction will be the exothermic one, and now I've told you that, well, unless entropy is too large, we need a way to quantitatively pick these two things apart. And that's why we need to introduce the new concept, which is called Gibbs free energy. Before we get to Gibbs, let's talk about, in the last 7 minutes of class, let's give some examples of entropy first, right? I think next class we'll start with Gibbs free energy, but for right now, let's talk about how could you predict entropy, right? So some general rules are available. The first rule has to do with molecule size. So if you have propane versus butane, what's the difference? Anybody take an OChem? Propane versus butane. Simone, what's the difference? You remember?
Propane has 3 carbons and butane has 4 carbons.
Yep, if I was going to draw it, I'd say 1, 2, 3, that's propane, right? There's a carbon here, a carbon here, a carbon here, versus butane, 1, 2, 3, 4, right? So it's the number of carbons, hexane, octane, all these are just telling you the number of carbons present, right? Which one of these has more entropy? Same? Different? The one with the longer chain. And what's the reason? Is it, I forget your name, Zion? What's your name?
Just call me Jimmy.
Jimmy? Jimmy. Which one has more entropy and why? You thought the longer one, right?
Yeah,
how come?
Because the molecule is more complex.
Because it's a more complex molecule.
So it has more ways to get right.
Yeah, think of like a tent pole. You guys they go camping. You got the tent poles and they're made of like little segments. That's pretty much like this, right? So if you have a short tent pole, like for the fly, versus a really long one, how much easier is it to tangle up the long one? It's way easier, because there's way more joints, right? That's exactly what happened. When you take a polymer and it can, like, every one of these can change its direction a little bit, the longer it is, the more disorder it can have, right? So bigger molecules have more entropy. That should make sense. Plus there's more atoms present, right? Each one of those has some entropy component. Okay, phases. If you have solid, liquid, gas, which one has the most entropy? Definitely the gas, because they're zooming around the room, they're all over the place. Liquid is like a more condensed version of that, right? And solid, it's probably even crystalline. Not always. A lot of materials are crystalline, some are. And then they're sort of locked in place. So the phase goes for solid, liquid, gas in terms of increasing entropy. Bonding. Forgot what I was going to ask about here. I usually have a clicker thing where I can show you. Let's skip it. Well, no. Is metallic or covalent bonding higher entropy? And why? Covalent is higher, somebody thinks? It's not that. Metallic's higher. Why would it be, though?
Because the electrons don't have to separate.
Yeah, remind me your name. Michael.
Because all the electrons are allowed to roam around freely, so they can.
Yeah. Think of the beach ball analogy, right? The electrons are bouncing around in this room, kind of like the beach ball. Whereas if it's covalent, two people are hanging onto it, and it has to sit between them, right? So there's more disorder possible there. All right, dissolution. If I take a can of soda We know that soda, whatever your corn syrup plus sugar, whatever you're wanting to drink, right? It also has CO2 dissolved in it, right? So when I open a can of soda, have I increased or decreased entropy of the system? Why? It goes back to the phases. We know that gas has higher entropy than a liquid, right? And a gas that's dissolved in a liquid also has lower entropy. So when you let that out, you've created more entropy, right? Fair enough? Fair enough? So that's dissolution. So if you were to undissolve something, basically, right? Normally you'd think that you've gone down in entropy, like Kool-Aid, right? If I took Kool-Aid and water and somehow were able to separate those two, I went down in terms of entropy. It got less ordered. And you say, hey, that can't happen. So why can the other one happen? Why can gas come out of a liquid? Why can it spontaneously dissolve?
Under pressure, it dissolves.
Yeah. It only dissolves under pressure, which means when you pop it, that gas then goes out. It's only because the product has so much more entropy. Gas has tons of entropy, right? That's the only reason this works. If the final product went to something that was ordered like a solid, it probably wouldn't happen. Like Kool-Aid powder doesn't go back to a solid because that's ordered. But going to a liquid, heck, or a gas, that's fantastic. Eric.
So with your soda pop can analogy, even though the entropy is increasing when you open it, the overall energy level is decreasing, isn't it?
Exactly. Okay, then last one, atomic mass. Heavier atoms have higher entropy than lighter ones. Why? Because they've got more electrons, right? If you compare uranium to hydrogen, it's got 91 more electrons. So it has 91 more ways that it can be disordered, right? Okay, so there's some rules of thumb for us to follow. Next up is Hess's law, and we're out of time, so we'll pick up here next time. But this has to do with adding these things together in a reaction.